achieve. Any questions from last time or anything like that? Or everything is going well with the course? So judging from the homeworks, so I've looked a bit at them, and it seems that things are going well with the course. It seems like everybody's doing well, doing okay. It wasn't, 100% for everyone, but it was pretty good. So I think so far we're doing well. So let's see, we have some different colors as well. There are plenty here. Okay. You had some strong preference about colors?
No. Hey.
Yeah. Okay. Yes. Okay, so I think you'll get your homework back on Monday, and also for you online. And they are graded from 0 to 10, which is some kind of indication of how it's going, and it will play some role in your final grade, but it's not, the end of the world. I mean, you can definitely catch up. I mean, you start to, have a wobbly start, but then you become expert complex analyst. I mean, there's nothing to worry about. It will count a little bit, but you can always catch up. The important thing is that you learn from the homework. It's just they complement the lectures in the course. And this is the idea. Okay, so today we're going to start a completely new topic.
Excuse me, I think you should start
the line in the middle, so this is the line.
I can only write here.
Yeah.
The camera only has this part.
Camera only has this part. Okay. Thank you. So that's a very small lesson. Could be in my office. Okay. So today we are going to, at least let me know if it's too small or I should also be in the picture. Yeah. Well, okay. I will sometimes be outside of the picture. I apologize for that. So we're going to deal with these conformal maps. And what would be the introduction for this topic? So we have seen so far, we've studied holomorphic functions, and we have seen that power series are holomorphic. We will see in the course that holomorphic functions are exactly those that can be expanded locally using power series. But all of this is fairly analytic, right? It's not a very geometric condition. It doesn't tell you very much about what we do. And speaking of it, by the way, I forgot to mention, we've of course also seen the Riemann Equations. That's a relation on the partial derivatives that, under sufficient regularity conditions, is equivalent to being holomorphic. By the way, on this note, I have this small document here, if somebody is interested, to really push the converse. So, holomorphic implies that the Cauchy-Riemann equations hold, but the converse is true only under some assumptions. We proved in class the Gauss theorem. For the homework, you got to see some examples to work out these boundary cases where you have insufficient regularity. And if you want sort of a small document discussing what would be the optimal results or some more optimal results than Gauss theorem in the other direction, so under what conditions does Cauchy-Riemann imply holomorphic, I have this, it's a small document discussing this. I will put it on Moodle for everyone afterwards. It's sort of a summary of work in this area by someone. So if you want to read the articles, you can look at the references in this document. So,
The one by Gray.
Sorry?
The one by Gray. Right?
Yeah, Gray. Yeah, some of you might already have found it, or maybe all of you did. Oh wait, can I take off my mask? Okay, thank you. So, since it's a smaller room, I felt I should ask. So now what we will do is give a more geometric interpretation of these Cauchy-Riemann equations, basically, but which will also be strongly related to the behavior of holomorphic functions. So we would like to give Okay, so geometric. Interpretation. I should break it, but I don't want to break it. Of the Cauchy-Riemann equation. Okay, and by geometric, again, I mean that so far we've only seen some abstract conditions on the partials, but what do they actually mean? And what they will mean is that Cauchy-Riemann, satisfying the Cauchy-Riemann equations will essentially be equivalent to being conformal. And conformal means preserving angles and orientation. And if you type that on Google, the first picture you get is this. So it means that, you look at this sort of square grid, and then you can map it in all sorts of simple or slightly more complicated ways in such a way that, locally, so you see that these lines here, they are still sort of parallel, even though we now curve, they are still, so to speak, parallel, which means that you preserve angles locally. And then you also should preserve orientation of these vectors. And we will talk about what this means. Another picture is sort of here. This is a picture of what happens when you take z equals f of z equals z squared, and then you map this square, which is mapped to such a shape here. And you see again that it will be conformal since you get this curved places, but anyway, these lines will be parallel. But so what is the reason? What is the link between these Cauchy-Riemann equations and preserving angles and this angle preserving property? And again, so locally, so because first of all, you might think when I say preserving angles, you might just think of a rotation or a scaling or something like that. But just to emphasize that all holomorphic functions will actually have this property. So many quite complicated functions will still be conformal. So it's not such a trivial property. After all, so the motivational example. So as a motivational example, let us consider, as we are used to, f, we write it as u plus iv. So this is a function. Okay, so u and v as usual. So our functions on R2, which are real value. And let's assume that this one is real differentiable. And it's real differentiable viewed as a function x from R2 to R2. So again, so we identify C, the complex plane, with R2, and the natural way x plus iy is associated with the coordinates x and y in R2. And then we view such a function as a function from R2 to R2, and we assume that it is real differentiable. Okay. So what does it mean to be real differentiable? Well, it means that you have in every point what is called often the total differential. So you have a function from R2 to R2. And the total differential, if you remember from calculus, what is it? It's a matrix, right? It's what's called the Jacobian. It's the matrix of partial derivatives. So this means that we have, and of course, this matrix, what it actually encodes is the linear map from R2 to R2. That is the differential. So it's this. Oh, sorry. I didn't want to write that. So first I wanted to, of course, write that. So we view this as a map that sends xy, u of xy, and v of xy. And then we consider the total derivative for being Jacobian, matrix, which is given by what I wrote. So f prime of z right here. So we sort of call it f prime of z. Map from linear map from R2 to R2. Which is what I just wrote. very soon, by the way, I will stop because this is kind of too much to write. So I will start calling these things ux, u sub x, u sub y, and so on. I will start calling this thing. I will start writing it ux, uy, dx, dy. You see it at least 3 times as fast. So I'm going to write it like this. So you have this linear map. So I mean, this is a linear map from R2 to R2 in this way. And now the question is, what does it mean to satisfy the Cauchy-Riemann equations? If you look at this, well, the Cauchy-Riemann equations is a relation between these 4 entries in this matrix. So the Cauchy-Riemann equations, they would imply that this matrix ux, uy, dx, dy can be written. So let me keep the first row. So of course I can write it. So let me keep ux, dy. But then I can write dx, dy in terms of plus or minus the quantities in the top row, right? So what I get here is minus uy, and here I get ux. So this is the Jacobian, the total derivative. We will often call it J. Okay. So we note that this is of the form, of a very special form. So it's of the form AB minus BA. The A and B will be, I mean, real value functions or real numbers. But at every point, our matrix will have this form. And what does this mean? So do you recognize, if you remember, sorry? Symmetric, sorry? Symmetric. So I would call it an orthogonal matrix. Is this what you mean? So, sorry, I didn't mean. Say again what you mean? I didn't understand.
Cosasymmetric.
Cosasymmetric.
Yes.
Okay. I don't know this terminology, unfortunately. But what does, let me ask you, what does it do? What is the action of such a matrix on vectors in R2?
Rotation.
Exactly. Rotation and just rotates?
Reflection.
Not reflection.
Orientation. Because determinant has rotation.
It preserves orientation, yes, but because it's a rotation, but it could also, if I multiply it by 2, it's still of the same form. So I have to also allow exactly. So I have to also allow scaling. So you were right. So it's rotation, but also scaling, and you are right that it preserves orientation because rotation and scaling preserves orientation.
Yeah.
Okay. So this is what's called an orthogonal matrix. Okay. So this. So now this map, I mean, such a map. This is a rotation and scaling. Okay, which are orientation preserving. And so this is the local behavior. So this gives the local behavior of x in some way. But I have to emphasize that it's local because this is what you get. This is the Jacobian matrix, which is the matrix of partial derivatives. So this is the linearization of the behavior of the function close to a point, infinitesimally close. So it means again that if you go and zoom in into these kind of pictures on this kind of grid at the bottom, then okay, it looks kind of like this. I mean, it will preserve. It will just be a rotation. So of course, the global picture can be that you can curve quite a lot. And if you type conformal math pictures in Google, you will find all these very beautiful pictures that look like flowers and all you want. I mean, what happens to these lines? It's a nice way to illustrate what happens to have a grid and then see how it becomes deformed under the map, but still keeping lines locally parallel. Okay, so this is the local behavior. So a conformal map so what I want to talk about is this conformality, and a conformal map is something that preserves angles the chair and orientation, and it does this locally. Okay, so let us just discuss what it could mean. I mean, let's just do it first with two examples or non-examples, and then we give a formal definition. So some example, of course, scalings and rotations are conformal. Okay. So scaling and rotations are conformal. Can you think of something that's definitely not conformal? I mean, there are so many examples, right? So if we take our standard example of a non-holomorphic function, this f of x, y equals x, f of z equals z plus z bar over 2, then this is, of course, not conformal because it collapses everything onto the x-axis, so it doesn't preserve angles at all. So this, if I write it like that, let me write it f of z is equal to the real part of z, is obviously not conformal, as it does not preserve angles. Since, of course, it maps the imaginary axis onto the real axis and it maps the real axis onto itself, so this 90-degree angle becomes enough. Okay, but what about f of z is equal to z bar? Okay, so this one is also not holomorphic, but so you might guess that this one will not be conformal. This one is sort of close to being conformal, but this one does not. But it's not conformal. And why is it not conformal? So let me draw this this picture here. Exactly. It does not preserve orientation. Why does it not preserve orientation? So let's see what it does. So if I take one complex number z, one complex number omega, and I look at the angle in between here, and then I get omega bar and z bar, then this angle here, so the angles are still the same if you just look at its size. But of course, what happened is that you flipped it so that you actually flipped the orientation here. And again, I will give a formal definition in a minute, and then you'll see what it actually means, I mean, the formal definition of flipped orientation. But you can see that these don't have the same orientation. So it does not preserve orientation, although it does preserve angles. Right? But this one is actually something that's called anti-conformal. Okay. So reverse this orientation and preserves angles. So this is called anti-conformal. Okay. So the only thing is that, I mean, it does preserve angles, it just flips everything. So it's strongly related to a conformal map. Will be called anti-conformal. Okay, and then the examples, if you want, I mean, any. So z goes to z2, or z goes to z, or z goes to e to z, and so on. Any holomorphic function is conformal. Okay, and this fact that any holomorphic function is conformal, we will prove it today. Okay, and we'll prove also, I mean, in the converse direction, what are the exact conditions for the converse rule. And it turns out that, okay, so any, okay, so what is wrong about what I just wrote is something that you have to remember. Any holomorphic function is, of course, not, it's very stupid, but any holomorphic function is, of course, not conformal because they could be constant, still be holomorphic, but constant functions definitely don't preserve angles, right? So any non-constant homomorphism. Okay. So formal definition of conformality. So formal definition. So let's take an open subset of C, but identified with R2, as usual. And then we say that a map F from A to C is conformal if the following holds. The first condition is that as a map, from A, so this open set inside R2 to R2, it is real differentiable. And again, being real differentiable means that this Jacobian matrix exists at every point in this open set A. B, F preserves angles. But now I will make slightly more precise what it means. So preserves angles between smooth curves, angles of intersection, by the way, I should say. Preserves angles of intersection between smooth curves. Okay, and I should tell you what the smooth curve is. So this is the moment where the course just for 10 minutes becomes a bit differential geometry. So in the course of differential geometry that you will have in the next semester, you will become experts in the differential geometry of curves and surfaces and so on, and all these tangent vectors to a curve and its parametrizations and so on and so forth. But now, of course, I will not delve into the details of all of this, but I will just present enough so that you can get a feeling and belief for what this definition is. So I will explain that in a minute. Let me just write the last one. The first condition is that F preserves orientation. Okay, so what it means to preserve orientation this is that the determinant of the Jacobian matrix is positive. So this is what it means to preserve orientation. Now, if you look at f of z equals z bar, what would the Jacobian be? It would be 1, 0, 0, minus 1. The determinant is 1 times minus 1 is minus 1, which is not positive. So this one is not orientation preserving, but it's actually orientation reversing. Okay. So explanation here for this star. So what does it mean to preserve angles of intersection between smooth curves? So first of all, there's some explanations from differential geometry here. So smooth curve. What is a smooth curve? So this is always a bit tricky. So smooth curve is some map going from taking a real number t and sending it to some gamma t with gamma 1 of t plus I gamma 2 of t. Since now if I want it to be something in the complex plane, I guess. So now it will be like this. So it's some curve starting with gamma 0, and here we have gamma of t, and all of this is inside C. And this has to be okay. So this has to be smooth. So saying that the curve is smooth means that this is smooth. And the usual word of warning in differential geometry is that, of course, everybody, if you ask someone, an ordinary citizen down in the city center of Trieste, what is a curve? They will say that this is a curve. Okay, we will start going, this is the curve. But the standard remark is that the curve is not actually the image, but the curve is the map itself. So in differential geometry, if I parameterize the same curve in a different way, so I say I want to go maybe from the endpoint to the starting point instead of the starting point to the endpoint, the image looks exactly the same, but as the differential geometric object, which is what we define as the curve, it's a different one. You know, if I reverse the sense of time, I want it to be different. I don't just want the curve to be the thing I draw on the blackboard. Okay, so a curve is a map, not its image. Okay, and then angles between curves is the angle between tangent vectors. So I want to look at the angle between tangent vectors. Okay, so color.
Okay, Stereographic.
No. Okay, so you have two curves. Here, I mean, can you still see if I go here? Maybe well,
Yeah.
maybe you'll have to move. I mean, like,
I was sitting there in the morning. This is
in that place, yeah. Okay. Yeah, so I mean, you have some other curve like this. So what is the angle between these two curves? So I have
in one there. You can.
So if you have these two curves, gamma of t and gamma tilde of t, but intersect at some point, right? So maybe they came like that, and then they intersect. So what's the angle of intersection? Well, they go in this direction. So what's the angle between these curves? So not to confuse you, let's just draw it like that. So the angle between these curves, so you look at the tangent vectors here. So here's the tangent vector, and here's the tangent vector. So we have a curve. Okay? So you have this tangent vector alpha to gamma of t, and you have a tangent vector beta to gamma tilde of t. And then you can look, of course, now you have two vectors, and you can look at the angle between these two vectors. And this is the definition of angle of intersection between two curves. Sorry for moving you around. Okay. So this is how you define it formally in differential geometry. So it means that we have to look at the angle between tangent vectors, and I call these tangent vectors alpha and beta. Okay. So the tangent vectors are obtained by differentiating. So you have this map gamma of t, and then you look at the gamma prime of t, and this will give you exactly the tangent vectors. But all of this you'll anyway learn in great detail in differential geometry. And this is complex analysis. So for now, let's just say this and tell you what it means then to preserve the angles. Well, then you will remember that if you take the scalar product, maybe I should continue in yellow. If you take the scalar product, then this is equal to cosine theta times the norm of alpha times the norm of beta. Okay, so what I want to do is that I want to preserve this alpha beta divided by the norm when I take the image of it. Because of course, if I preserve this quantity, then I preserve cosine theta, and this is actually enough to say zero. Okay, so I want to preserve this under F. So what does it mean to preserve it under F? Well, okay, you have these two curves, and then they will map to two different curves. So the image of the curve is a curve. So we look at, and when we look at the tangent vectors of these, you know, you had these curves over there, and then we are mapped to S of gamma of t and F of gamma tilde of t, which are again two curves. And of course, the point where they intersected, they are still going to intersect because it's the image of the same point under the function f. And then you look at these new tangent vectors here and look at their intersection. So look at tangent vectors of f of gamma t and f of gamma tilde of t at t equals 0. T equals 0 is, of course, this point of intersection by my convention, the way I set up things. So this is given. So this is something that you can check and understand the differential geometry. So given by multiplication by the Jacobian, so preserving angles means precisely that. Okay, so what I'm saying is that the tangent vectors here are exactly j times alpha and j times beta, where j is this matrix of partial derivatives. Okay, so of course alpha and beta, they were ordinary vectors in R2. I multiply them by a matrix. I get this Jacobian matrix. I get two new vectors in R2. And take this as a fact if you want, try to understand it from differential geometry. The tangent vectors here are exactly j times alpha and j times beta. And now preserving the angles, so what I will set as a definition, I will use the scalar product and the norms. I will say that if I take j alpha, j beta everywhere here, this is equal to this. Okay, so this is what it will mean to preserve angles. Okay, preserving angles means that. Preserving orientation means that the determinant of the Jacobian determinant of j is positive. So this is the definition of conformality. If you have a differentiable in the real sense map that preserves angles and orientation in this way. Okay, and we already checked for f of z equals z bar that the orientation preserving thing did not hold. Now, okay, so let me erase this. Are there any questions before I? Unfortunately, I have to erase very quickly since the blackboard is so small. Yeah. Okay. So I will soon write down the main theorem for today. So all of this is in the notes if somebody did not have time to copy or so on. Of course. Here we go. So now remark. So a map satisfies condition A, so differentiability, and condition B, which is angle preserving, but not C, is called anti-conformal. Anti-conformal. And the prime example is, of course, f of z equals z bar. And then we have the following exercise. I don't think it will be on the homework, so don't worry. Just take it as a fact. So any anti-conformal map is of a form z goes to f of z bar, where f is conformal. Okay, so the trivial example is again f of z equals z bar. It's equal to f of z equals z, which is conformal, and then you take the quantity. But what this means is that if you were interested in anti-conformal maps, but you understood already everything you wanted about conformal maps, then the study is essentially the same. It's a mirror on the other side of the study of conformal maps. So using this fact, we just say, okay, anti-conformal maps exist. They behave sort of in the same way, but we just reverse orientation, flip orientation. They are always of this form. So now let us focus on conformal mass. Okay. So this is the case. So let's now write down the main theorem. So the main theorem of today is that, so it's going to be about relating conformality to solving Cauchy-Riemann equations and by extension to being holomorphic. Okay. So if x equals u plus iv, it's conformal. In A, some open subset of C. Then the Cauchy-Riemann equations, which I now write CR, but everybody understands what I mean. Then the CR equations hold. Okay, so ux equals to uy, and uy is equal to minus ux. But also conversely, we have a converse to this. If instead of being given f, and then showing that if we decompose it into u and v, then the Cauchy-Riemann equations hold, we can also say, what if we are given u and v? So if u and v satisfy the CR equations, and okay, we need some further property. Just like when we had holomorphic implies Cauchy-Riemann, but when we wanted the other way around, we had to say Cauchy-Riemann plus some sufficient regularity on the partials, or sufficient regularity somehow of u and v, then we get the converse. So here, this is kind of like Gustaf's theorem, right? So it's some kind of analog to this. So, and we assume that ux, uy, dx, dy, so all the partials, they exist. And not only do they exist, they are continuous. Then f equals u plus iv is conformal. And it's conformal. Yeah, okay, so it's conformal unless it is constant. So it's very easy to forget this. During all these lectures, conformal maps are definitely, constant maps are definitely not conformal. So all of this will always be true, unless definitely always unless they are constant. Because the problem with this kind of statements is that, of course, the constant map does satisfy the Cauchy-Riemann equations trivially. 0 equals 0 equals 0 equals 0. Okay. And just as a remark, why do we always have this condition that the partials exist and are continuous? Well, the reason is that this condition, this is the standard condition that implies the real differentiability of the function in the sense of origin. It implies that this Jacobian exists. So just the existence of the partials doesn't imply actually the definition of real differentiability. So this is a small subset. So we do need to use this continuity to use this fact from analysis. This ensures that our function will be differentiable. Okay. So in other words, for regular enough functions, so this is a remark. Regular enough functions, f conformal if and only if f is holomorphic, and this is true if and only if the CR equations hold for f. Okay, so under this regularity assumption, you remember this is the same regularity assumption as in the SAS theorem. So in particular, if we assume this, then everything is equivalent for non-constant holomorphic functions, right? So non-constant holomorphic functions will be, again, this remark does not allow it to be constant. Otherwise, it's equivalent. So more precisely, so this is a fact. We will do more of these things. Actually, we will revisit the conformality after we've done integration, because then we can do many more things when we have all the tools. So the fact is actually that, I mean, so in particular, well, holomorphic, yeah, so let me write it. So holomorphic no, let me just write the fact. So let me fact. The fact is that if you have a holomorphic function and f prime of z is never zero, so if the derivative never vanishes, then this is equivalent to f being conformal. Now, this condition that the derivative never vanishes is very curious one in complex analysis. In real analysis, okay, you say the derivative. What would it mean if the derivative vanishes? If we say it in the converse. So the derivative being zero in real analysis is not such a big deal. But in complex analysis, this is quite a strong condition. Yeah, of course. Yeah, feel free to move around. I mean, so no worries. Okay. So this is a statement of what you could call the conformality theorem or something like that. Maybe it has a name. As usual, I won't know the name. I know some names, but most of them I don't. Okay. Of these theorems. So. That's it. So let's see the proof. Let's see the proof of this theorem. So first, suppose that F is conformal. And what we want to do is we want to show that the Cauchy-Riemann equations are satisfied. Okay. So then, by definition of conformality, it's in particular differentiable, so I am allowed to write down this matrix. And then I will choose two vectors. So earlier I was calling alpha and beta the tangent vectors, okay, of some curve. Now let me call this alpha, let me call this beta, okay. New notation that happens here. Let me consider the column vectors here. Dy. So let me consider these vectors. And then, so these are column vectors, of course, of J. And by definition, the multiplication by J is preserving angles, because this is what it meant to be conformal, right? That when you multiply by this matrix, it's conformal, by the definition I went through. Multiplication, yeah, let me write the full sentence. Multiplication by J preserves angles. So what can I do with this? So in particular, if I look at any two vectors where I know the angle, any two vectors, let's say where I know they are orthogonal, then when I apply J, they will still be orthogonal in the image. The image of the first will be orthogonal to the image of the second. So in particular, I know that 1, 0 is orthogonal. So I'm now dealing with vectors in R2. I know that 1, 0 is orthogonal to 0, 1. Okay. And then if I look at the image, so it implies that j of 1, 0 is orthogonal to j of 0, 1. But what is j of 1, 0 and what is j of 0, 1? If we look at the definition of j and
Sweet.
okay,
J 1 0 is column vector huge sweet.
exactly, it's UXV. So it's alpha, right? Yeah. So this thing is alpha, and this thing is beta. So in the same way, as you see if you multiply this thing. So this is alpha, this is beta. So this means that alpha is apparently then orthogonal to beta. Okay? So this we have shown. So similarly, okay, so if I look at j of 1, 1, it must be orthogonal to j of 1 minus 1. Because again, 1, 1 and 1 minus 1 are also orthogonal vectors. If you try to picture how they are. But now what is j of 1, 1 and what is j of 1 minus 1 in terms of alpha and beta?
Alpha is beta, J 1 1.
Exactly. So this is alpha plus beta, and this
Alpha minus.
is alpha minus beta. Correct. So this means that alpha plus beta is orthogonal to alpha minus beta. Okay, so now I'll be forced to erase this, but please, I think you can remember it. Okay, so they are orthogonal. So now what can we do? By definition of orthogonality, if vectors are orthogonal, if only the scalar product is 0. Right? So this means hence the scalar product of alpha plus beta and alpha minus beta is 0. Okay, but on the other hand, this is also equal to this. And this is equal to alpha squared minus 1 beta squared. And what does this say? Well, it says that the norm of alpha squared is equal to the norm of beta squared. But these are just positive real numbers, so this means that norm of alpha is equal to the norm of beta. Okay, so in the end, we know that alpha is orthogonal to beta. So, and also we have the same norm. So this means, so to summarize, alpha is orthogonal to beta, and alpha, norm of alpha is equal to the norm of beta. And now we have to think about what this means for vectors in R2. So since these are vectors in R2, so let us think. So if I have a vector here, so let me draw the coordinate system, and I take a vector here which is AB, let's say. So this is A, and this shorter side is B. Now when I rotate it 90 degrees in this direction, then what I will get is something where, now A is this side, right? So A is here, and this length here is B, but it means that this vector is minus B A, right? And if I draw the other vector here, so if I rotate it in the other direction 90 degrees, then the vector I would get, so it would be B minus A. Okay. So what it means that alpha is orthogonal to beta, and that they are of the same norm. It means that this vector here is equal to one of these vectors. So let me see. Let me write really what the statement will be. So this means that alpha, which is what I write down here, is equal to plus or minus so this is alpha, just to make it clear what I'm doing. So this is alpha, and this is rotation. So plus minus rotation of 90 degrees of beta. Okay. Right. So this is what I get. I guess this is the one clever step in this proof. But what does this mean? This implies that the determinant of this Jacobian matrix, so it's equal to up to this sign, which I don't know yet which one it is. Okay, so this is equal to determinant of ux, uy minus uy ux, which is equal to plus minus ux squared plus uy squared. Okay, so of course, what I did here was simply, I take the definition of J, and then I replace, so I know that ux is equal to plus minus ui, and I know that this is plus minus this one with the corresponding signs. So then you can see that the determinant has to be plus minus of this, which is plus minus of this. Okay. Is it clear? So you have this, but F is conformal. But F conformal implies that this has to be positive, right? F conformal implies that the determinant is positive. So is it clear what I did here in the last step? Okay. So determinant is positive, and that means that we have to have the plus sign, right? This is plus minus, and this is a positive number. So it means that so determinant of J positive by the fact that it's conformal means that it must be equal to plus this ux squared plus uy squared. So it's exactly equal to that. Okay. And this implies in particular that, okay, the determinant was this because plus minus was depending on which choice we have here. Sorry?
Equal plus.
Exactly. So it's equal plus. So it means that since we had to have a plus sign here, the plus sign there came from choosing the plus sign here. So then we have to have plus here. So it means that ux dx alpha is equal to vy and minus uy. But now what is this? This is exactly what we remember. We get out of this argument because Riemann equations. Assuming that F was conformal. Because thanks to F conformal, we have this determinant positive, and we have many other things. So of course, the preservation of the angles that allowed us to even start the argument. Okay, so now for the converse, if we want to assume now that the Cauchy-Riemann equations are satisfied, how can we show that the corresponding map F equals u plus iv has to be conformal? So then, so suppose Cauchy-Riemann equations are satisfied for u and v. Then, so under the irregularity conditions, so this is where we use it. So because of irregularity conditions, the partials, we assume that the partial derivatives exist and are continuous. So then it's totally differentiable, which means that we can write down in particular this matrix. So we can write down this by the hypothesis, right? Because if we assume nothing on u and v, these might not exist. But we assume something. We have to have enough regularity. So these ones exist. But now we didn't assume conformality, but what we did assume was Cauchy-Riemann holds. So if Cauchy-Riemann holds, then we can rewrite this using the Cauchy-Riemann equation. So we can say we keep the upper row again. And then we say that Vx is equal to minus u of y and Vy is equal to ux. So you get this kind of matrix. And then we go back to this motivational example I did right at the beginning, where I said this is of the form A minus BB, right? And then we said such a matrix was an orthogonal matrix. I mean, it's a so-called orthogonal matrix, actually. It's a rotation and a scaling, we said in the beginning of the class. Any matrix of this form, where these are the same, and this one is minus the other. Okay. Okay, but so first of all, let me put alpha to be these column vectors. So alpha is ux now minus uy, and beta is equal to uy ux. Okay, so then alpha, if I take the scalar product between these, then this is equal to ux uy minus uy ux. But this is 0. Okay. These things. So this means that alpha is orthogonal to beta. And the fact that it's orthogonal to beta is exactly what I meant earlier. You could have recognized this immediately, but now I should have proven what it means to be an orthogonal matrix. So this means that J is an orthogonal matrix. It's in O of 2. Okay. So this is an orthogonal 2 by 2 matrix. Okay, and I don't know how familiar you are with these orthogonal matrices, special orthogonal matrices, and so on. But we don't really need much for it. So let's just also note what is the determinant. The determinant of this matrix is ux squared plus uy squared, which is in particular positive. Okay, and this will imply, so using just a tiny bit of what we remember from the linear algebra. Okay, so this means that J is positive, which means I can take the square root, by the way. Now, this is not the square root from last time. Okay, it's just the usual real square root. So ux y squared times t, where t
These are the normal.
yeah, so t is in SO2, which means special orthogonal. So means determinant of t is equal to 1. Okay. So it's an orthogonal matrix with determinant 1. Where t is then acting by rotation. But then, yeah, so what I'm saying is that t is special orthogonal, so it's just a rotation. But then you also rescale possibly by this positive factor. So the total effect of the action of this J is that it's rotating and scaling. Okay. So it's a rotation and a scaling. Okay. And it's scaled by, of course, this factor. Okay, and since it's a rotation and a scaling, this J, then this map F is conformal. Okay. So this ends the proof. Here, that is good. Yeah, and I already told you about this this fact that f is actually conformal if and only if it's holomorphic and its derivative does not vanish anywhere on A. So this will clarify to you more precisely the relationship between holomorphic and conformal. Because this theorem passed through the Cauchy-Riemann equations, but as we know, we lose sometimes a little bit of information there because we need to assume the regularity to get the converse whenever we go to Cauchy-Riemann. So the true statement, but since I already wrote it, I won't write it again, is that f is, so holomorphic and conformal are essentially the same thing. So as long as holomorphic and derivative is non-zero, then this is precisely what it means to be conformal. In particular, a constant function has derivative 0. So it will not apply. Okay, so that was the introduction about conformal functions. So we're conformal maps. We're going to get back to this in a second. But what I want to continue with, unless there are any specific questions on this right now, is to continue with considering rational functions. So quotients of holomorphic functions, and this will be very natural to do. What will happen, of course, is that if you have a rational function, then you could have a 0 in the denominator.
Poles.
Exactly, and then you get this thing that's called poles, which is that the function takes the value infinity. Okay, but of course, doesn't take, yeah, so it's singular. But this one would be naturally defined on the so-called extended complex plane, so where you take C and you add a point at infinity. Since you took topology, this would be the one-point compactification of the complex plane. And this one-point compactification is exactly what is called the Riemann sphere. There are many names for this object. It's just a sphere, but it's called the Riemann sphere in this context. Okay, so that's it. So now the next topic. The Riemann sphere and rational functions. So actually, what I want to talk about now in the next lecture is the Riemann sphere, and then I will focus on the Möbius transformations, which is the simplest kind of rational functions. And then we will go back and feed to a more general, a bit more advanced theory of poles and a bit more generality slightly later in the course. Okay, so recall, of course, let's see a symmetric space which is not compact. Okay? The distance is just given by the absolute value. But the point here, what I want to say is that it's not compact. Of course, this you know, it's just R2, which is not compact in this sense, with this usual Euclidean metric, right? Okay, so this we needed to recall for this point of view that I will take. Okay, and so just as a small introduction to this Riemann sphere, so we saw many examples of analytic functions. To get further examples, we could look sometimes at quotients. Okay, so this would be a natural thing. So if f and g are two functions which are analytic on some open subset A, C, then this implies that if I look at f over g, if I look at this quotient, is it analytic? Well, okay, not everywhere in general, right? They have to take into consideration the zeros of g. So this one is analytic on A minus the set of zeros of G, if I just write it like that. So let's set of this, we have that equal 0. Okay, and so a simple kind of such functions would be the rational functions, of course. So for rational functions, we take P and Q to be complex valued polynomials with no common zeros. We already writing it on the simplest possible form. Okay, so then P over Q, so let me call R P over Q for this rational function, is analytic, as we saw on all of C minus the zero set of Q. And moreover, if Q of A, so if we are in such a point where Q of, in a point A where Q has a zero, okay, so Q of A is equal to 0, then what happens is that if we look at this limit of P and Z over Q of Z, then what does it equal? It equals infinity. Okay, and of course I have to write this no common zeros, otherwise that would not be true. Might be things maybe canceling out at the time. Okay, so then this is equal to infinity. And now, so we would like to define. Yes?
PA may be also equal to 0. Then
Exactly. So this is what I meant by no common zeros. It means that if Q of A is equal to 0, then P of A is not 0.
both of P and Q and
Yeah.
its degree is same.
Yeah.
P Z minus A or degree K, yeah, the same. Then concrete number, then concrete number.
Yeah, then it's a concrete number, exactly. Yeah. Yeah. So this is why I wrote this this no zeros. So of course, you're at in general, you can write it, and you have sort of 3 different cases. Depending on the degrees of the numerator and denominator, it can be a 0, it can be a some number, complete number, it can be infinite. But in this particular case that I wrote down, where there are no common zeros, then it's infinite. Okay, so this is just as a small motivation I mean for now. So what we want, so the point is when this happens, is that we would like to define. So this rational function R, which is P over Q, it's defined on C, but you took away some bad points, right? The zeros of Q. And we don't like that. I mean, we would love to be able to extend it to all of C in a natural way, okay, but we can't because it goes to infinity in these points. But what we can do is we can introduce a larger space. We can take C and we add 1 point, which is the point at infinity. And we want to say that then R of A is equal to infinity. What we want is to define R of A equals to infinity. I will tell you, I mean, make rigorous what this means. So we want to do this in a sense, in a way so that the function we get, the extended function, becomes continuous on this extended complex plane. Okay, so we want to define this. So my remark is that it's useful to consider that rational functions. This is just a point of view, right? But it's a very powerful and useful point of view. So consider that rational functions take values and even are defined on C hat. So this will be my notation for the extended complex plane. This is the extended complex plane. Or another way of saying it is the Riemann Sphere. Okay. So all of these ways of writing or saying are the same thing. Okay. In the end, and if you know some complex algebraic geometry or something like that, it is even also equal to CP1, which is equal to complex projected, a complex projected line, okay, or complex projected space of dimension 1. So if you don't know what that is, don't worry, but this is something also very classical. If you do complex geometry, you basically start by studying CP1, which is then nothing but if you don't know what projected space is yet, you'll learn it eventually during your way through mathematics. Okay, so anyway, what we want to do, this was just to motivate as a small introduction, why we want to introduce this object here, C hat, which is the 1-point compactification of C by adding 1 point at infinity. Of course, be mindful that there is only 1 point, there is only one infinity, there is no plus infinity, there is no minus infinity, right? Because, I mean, first of all, C is not an ordered field, so whichever direction you go, exactly, everywhere you go, it's the same. And this will be very clear in the picture, because actually the picture of this C hat will be just, this is why it's called the Riemann Sphere. This is C hat, and the point at infinity by convention is this. Okay, so as you see, wherever you're going, there is only one infinity, and it's this point. So this will give a formal picture that I will now explain. Okay. So, the Riemann sphere. Riemann sphere, we have difficult to see anything. So first of all, topologically, what is it? So topologically, it is just S2, which is the unit sphere in R3. Okay? So topologically, it's just what I drew here. The unit sphere. This is the topology. But then, just word of warning, I mean, I will put a metric on this, and the metric will be completely different from the usual metric on C. So this identification will be different. Okay? And this will turn out to be a compact topological space. Exactly, the Chordal metric. So the picture here is the following. So it's a bit hard to draw, I always thought. Try. I'm trying to draw. Nice sphere. I don't know, it's horrible, but yeah. Anyway, I'm sure you can understand what I want to draw. Apologize for the drawing. So let me just draw it like that. Okay, so what I'm trying to say is that you have this this sphere, and then this yellow equator here is cut through by the complex plane. Okay, so this is S2, and this is the complex plane, and it passes through the equator. So there are actually two conventions for this, right? So depending on who taught you your first complex analysis course before, or which book you happen to pick up, sometimes this sphere sits on top of the plane. But okay, now I will use the convention that it goes through the equator. You can do either one. It will give you slightly different formulas though. So don't use the formula from one book one day and the formula from another book another day. Then it will be wrong, unless they use the same convention. So now we use this convention. It goes through the equator. This. Okay, so I managed a slightly better picture here. When I drew it. Okay, so let's do that. Let's do that. Let's do that. The x-axis, the y-axis, the z-axis in R3. Okay, it's already improving a little bit maybe. So this is the center point here. This is the origin. And then what we want to do is I want to introduce now this thing called stereographic projection. So this is what oh yeah, and there's a special point here, very special point, which is this, which is called M. And M here is often called the North Pole. And it's just the point 0, 0, 1. Okay, of course, you can understand why it's called the North Pole. We do everything by analogy to that. And this North Pole in the Riemann sphere is exactly what we will call infinity. Okay. If you want to go and visit Santa Claus, he lives at infinity. That's why we don't see him. So now we have a bijection. From S to minus, so if I take away this point N and look at all the rest of the sphere, just minus this one point, then there is a bijection naturally between this and the complex plane here, which is given by stereographic projection, given by what is called stereographic projection. Okay, so let me tell you what this is. So stereographic projection, first of all, we can draw it. So the map is defined as follows. So you take the North Pole, and then how do you associate a unique point in the plane? Well, what you do is that you take a line that goes, so you don't start by going, up. So I stand in the North Pole, I don't start by going up. No, I take a line that goes into the sphere, okay? So it goes into the sphere. And then when it goes into the sphere, of course, it has to come out as I continue. It will always hit the boundary of the sphere at a unique point. So then it hits the boundary of the sphere at some point. So, I just went, I stood in the North Pole, I went in, and then I came out in Trieste, and then I continue until I go down and hit the complex plane. Or of course, it could happen that they hit first, since the plane goes through the equator, I could hit the plane first and then I could exit. But anyway, on this line that they draw from the North Pole, there's only one intersection point with the sphere and one intersection point with the complex plane. And I will associate them to each other. I will associate to this point. Or you might think that to this complex number, I associate this point on the sphere. Okay? And this point I will call x1, x2, x3, because this one lives in R3, so I need 3 coordinates. This is a point in R3. I hope you can see this. And this one is something. So this is the point xy0. Okay, since all this picture is inside R3, I use also the third coordinate, but of course we will think that this corresponds to z equals x plus I1. Okay. So I have x, y, and 0, and I associate it to x1, x2, x3. Now, there's a convenient formula to define this formally and not just through a picture. What is the formula? How can I write x1, x2, x3 in terms of x and y, and vice versa? If I'm given these 3 coordinates, how can I find these 2 coordinates? Yeah, so what I have to do is I have to write down some kind of system of equations, right? So what it has to satisfy these points. So stereographic projection, so it's exactly the one. So actually, you can stereographic projection, it makes most sense if it's the one sending this point down to that point, but you can also say that it's the map in the other direction. Okay. So sending anyway, so let me write it like that, sending x plus iy which corresponds to this xy0 to the point x1, x2, x3. And it will do this in such a way that we have the following. I mean, all that I've said in words, we'll now write it down as a system of equations. So first of all, I want them to be on the same line, passing through the North Pole. So how do I write that down? Well, I want x1, x2, x3. If I take that minus the North Pole, 0, 0, 1, then what I have is this direction here, this line. So I want this to be a multiple lambda times, if I take xy0 minus 0, 0, 1. So this condition means that we are on the same line. So on the same line. The one that I drew. Okay, so and this is true for some lambda, of course. So this is what this says. Then the second one is that I want to specify that this x1, x2, x3 has to be on the sphere. So being on a sphere, it means that that it satisfies this equation because it's on the unit sphere. Okay, so it's equal to 1. Yeah, maybe I didn't write it. Yeah, I did write it. It was the unit sphere, not 3. And then I also want to tell you what x and y are and what is my relation with everything with these complex numbers. Z is equal to x plus iy. So now I've told you everything defining this this map, this 1, 2, 3. Okay, and 1 and 2 together means that x1, x2, x3 is the unique intersection point with the sphere of this line going from xy0 to the North Pole. Okay? And then, so we can get the formula now. For x1, x2, x3, in terms of xy. So how do we do that? Well, so we saw the system. So x1 is equal to, so now we just look at this first condition and rewrite it. What does it mean? Okay, so we have x1 is equal to lambda x. And then we have x2 is equal to lambda y. And then x3 minus 1 is equal to minus lambda, right? So x3 minus 1 is equal to minus lambda. So we have this system with these three equations. So this comes from 1. Okay. And then under the additional constraint, okay, I could have written this as a fourth equation in here, of course, but now I wrote it like this. So under the additional constraint that, okay, x1, x2, x3, they are on the sphere. So if I rewrite it in terms of x and y, then we have to have lambda squared x squared, so this is lambda x squared, which is this, plus lambda squared y squared, so lambda y squared is here, plus x3 squared, well, x3 squared is equal to 1 minus lambda squared, is equal to 1. Okay, this is condition 2. Okay, so doing this, then we see that this is equivalent. So this additional constraint here, this thing over here, so this is equivalent to saying that because x squared plus y squared, in terms of z now, if I want to write it in terms of my complex number, x plus iy, then it's just the modulus, right? The absolute value. So this means that lambda squared, the modulus z squared, right? And then I develop this parenthesis 1 minus lambda squared. So plus lambda squared minus 2 lambda plus 1, and then I take the minus 1 from the other side, is equal to 0. I have some cancellation. These things cancel. And then, okay, let me continue. It's a shame to erase such a picture, such hard work, but let me try to keep it for one more second. So then what we get so what we get is that lambda, what is down there, we get that lambda times module of z squared plus 1 minus 2 equal to 0. And I guess I will be forced to erase it. Okay, so this is equal to 0. And this means that either we have these two cases. So if lambda is equal to 0, this would correspond to x1, x2, x3 equals 0, 0, 1 is equal to the North Pole. Okay. And in the case that lambda is non-zero, then this implies that lambda is equal to 2 over 1 plus mod of z squared. Okay, so what's inside here is equal to 0. So this is equal to 0. You rearrange it, you get lambda is equal to this. Okay. Good. So this means that lambda is equal to that. And hence, if we plug lambda equals to this into these equations that I have here, x1, x2, x3, so of course I could put the 1 on the other side, x3 equals 1 minus lambda, then what I get is that x1, x2, x3, if I write it in this way, is equal to 2x over 1 plus mod z squared. So maybe it's not so beautiful to mix x and z in the same line, right? So maybe if I want to be slightly more elegant, I could write real part of z here, right? Or I could write here x squared plus y squared. So 2 real part of z. Here I have 2 imaginary part of z over 1 plus z squared. And in the last coordinate, I will have this. Why do I have this in the last coordinate? Well, this thing is just equal to 1 minus lambda, which is equal to 1 minus 2 over 1 plus mod z squared, which, if you do the math, is exactly that. Okay? So this is what you get. And moreover, okay, so this is the formula. And moreover, since x, so in the other direction, we have that x is equal to x1 divided by lambda. Y is equal to x2 divided by lambda. Lambda is equal to 1 minus x3. This gives that z is equal to, in terms of x1, x2, x3, we also get, so of course, here we said, okay, give me z, and I'll give you x1, x2, x3, the point on this field. Now, conversely, if you give me x1, x2, x3, then what's the formula for z? To give me a point on the sphere, then this formula will be equal to, again, just by using these 3 facts and plugging in what we know, you get that it's equal to x1 plus I, x2 divided by 1 minus x squared. Okay, so this is, I guess my time is up. So I should stop here. And the next thing that we want to do, so now we prove these formulas. So the next thing is to introduce this chordal distance and say something about this extended complex plane, this Riemann sphere, as a compact topological space with this new metric, this new chordal metric, chordal distance. And then, yeah, and it will be on the homework, or there is already on the homework, this formula to prove for this chordal distance. But I guess this will have to be on Monday. Actually, hang on, let me just. Okay, I changed my mind because since I know that homework is always tight to have enough time to do everything, I would really like for you to be able to do this over the weekend. So let me just say that we can define a new distance on this C hat using the Euclidean distance R3. Okay, and this will be the chordal distance. So if we let S so now in my notes, I use this convention that the stereographic projection goes from the complex plane up to the sphere. Maybe this is what you'd like to call the inverse of the stereographic projection, okay, but it doesn't matter. It's just the name. So let this be the stereographic projection. So the projection map that I just defined and gave formulas for. Okay. So the one that sends this element down here to the intersection point of the sphere, which will not be the North Pole. So then we say that the chordal distance, so the distance between 2 points in the complex plane, Z and W, so this is the chordal distance. This is defined to be the distance between S of Z and S of W. And this is the Euclidean distance in R3. So the picture is very simple. So you have this thing here, then you have your sphere. Okay, and then if you have 2 points, Z and W, then you draw these 2 lines, okay, and you get 2 intersection points with the sphere. And the distance between Z and W in this new metric, the chordal distance, is equal to the Euclidean distance between this point and this point. Not along the sphere. So if we were trying to measure the distance of the surface of the Earth between Trieste and Lahore or something like that, we wouldn't follow the surface of the Earth, but we would go this straight line through the crust of the Earth. No, we use the Euclidean distance.
If we move
over
sphere, we can.
No, so this is as points in R3. We want to look at the distance. Okay, and then you can prove, and this is the homework, that this chordal distance of Z omega is equal to 2 times absolute value of Z minus omega over square root of absolute value of Z squared plus 1 times the square root of absolute value of W squared plus 1. This is an exercise which is a little bit messy, and you will definitely go and look in your books and you will find things written about that. But it's the last exercise in the homework. It is a bit of a mess, but it's still nice to look at it. So now that I've said that, if I stop now, the only exercise that you cannot yet start doing on the homework sheet is the one, I don't know, number 6 maybe, or 5, the one about Möbius transformation. And we will go through that next time. All the other exercises you can now do. Well, yeah, but we're 2 exercises about merger section. So yeah. So this will have to wait until Monday, when we will go through. We'll finish this. By the way, showing that the stereographic projection from this Riemann sphere is actually a conformal map. Okay. So this is something you can think about. And then we will go through these Möbius transformations, and we will show in which way they map regions to others and so on. In which sense they are conformal. Okay, so now what's up? Any questions?
It is conformal, and this metric.
Yeah. No, so it's conformal in the usual sense. I mean, of angles measured in R3. So it means that if you take 2 curves here, then it's actually, if you look at the sphere, so you take the sphere, and then you take circles here. So it turns out the circles map to lines or circles in the complex plane. So if you take the circle here, you take the North Pole, and then you take some circle through the North Pole, and it comes back on the other side, like that. You take one of the great circles, maybe. Then what does this map to? If this goes through also the South Pole. Yeah. So then you follow, if you try to get to this geometric intuition, so you try to project to this point that is right very close to here, it will be very far away in the complex plane. And this point, it will be just already in the center. So this will be the origin. So this will actually have as an image a line. If you took some other circle here that maybe goes like that, so not a great circle, then the image would be, if you can imagine what would happen to such a circle, if I take a circle around Europe or something, coming back to the North Pole and then back, then the image would be a circle in C, if you can see that, if you can imagine that, through this stereographic projection. And and what I wanted to say is then that what it needs to be conformal is that you take some circles starting there, some circles starting there, then you, in the same sense as before, of differential geometry, you can look at the tangent vectors in this point to these curves. It has an angle that is well defined. Then you look at the image of these. So they mapped into one mapped into some line, one mapped into some circle, but anyway, at the point where they intersect, they have some also tangent vectors. You have an angle in the usual sense between these tangent vectors, and this angle is the same. So this is the meaning of stereographic projection. And this point, I think, is quite easy to see. I mean, you can easily video it. I mean, it's just try to picture.
Yeah.
I mean, we were discussing this the first lecture. Do you have a geometric intuition, or do you not have a more algebraic intuition, and so on? But I don't know. At least, I mean, for me, this is the kind of thing I always like. So for me, this is sort of, you see it, but maybe,
Professor,
yes.
is there any interesting properties that we can get if you project it on the complex plane instead of the real plane?
So we are projecting it on a complex plane.
Yeah.
Yeah.
What is the difference if we project on the real plane?
So, I mean, so far what we're talking about stereographic projection is a geometric construction, which doesn't have anything to do really with the complex structure. So if you want, we are projecting from the sphere to the coordinates xy in R2, identified with xy0. So far we haven't actually done anything in complex analysis with this.
Actually, this is a homeomorphism. This stereographic projection is a homeomorphism between, it's like if you pick up the North Pole, and then this is just homeomorphic to plane.
Yeah. So it's sure. So I mean, it's a nice map with nice properties, which is a bijection between S2 minus the North Pole and the complex plane, but also, of course, R2. So I mean, so far we haven't used anything. So really, when you start doing complex analysis, it's more like basis identification. You can go and do complex geometry and say that this is a complex projected line and so on and so forth. But I mean, this comes sort of after this work. So far, all the properties you have them marked. No. Any virtual questions, maybe? Oh, I see something. By the way, should I have pressed record in this room? Should I? Okay. Yeah, so I'm not entirely sure if I actually.
I think we're not supposed to.
I think they're recorded.
Yeah.
Because when I
Yeah, because it's different because we are recording. Yeah, we are recording the Zoom. Yeah, it's still recording. Good. Yeah, because last year we used to press these buttons ourselves and then it would record, but nobody was on Zoom, so it was differently. Okay, good. So I hope the homework is not too much. I know some people told me it was a bit too much work and so on, a bit too long. I keep that in mind, but I also don't want to remove all the extra charges. I don't know.
It's not democracy.
That's what?
It's not democracy.
No, I mean, that's kind of better. Yeah, I mean, I could say, okay, it's too much. Let me just take away the exercises. But they are very simple. You can learn the things. So at some point, you should do that. Anyway. So I keep them.
Fortunately, they are not 4 course assignments.
Sorry?
Fortunately, they are not 4 courses assignment together.
Yeah. No, but it's interesting also because I asked the students from last year, do you think it was too much? Too much work, my exercise? And they said, no, it was fine. But actually, the difference was that you have real analysis at the same time, and they didn't. They had another course at the same time, and real analysis is more homework than that course, which was the algebra course, which has less homework. Yeah, apparently, Emmanuel and I give more homework. Yeah, but we don't know that because we just go to our own lectures. We don't sit in all the other lectures. We have no idea. We think everybody. Yeah. Well, anyway, yeah, I hope it's okay. I mean, if it's really too much, I will start saying that we'll only grade the problems 3, 5, and 7 or something like that. Would probably be my solution. But in any way, I mean, either way, you should solve all these problems before the exam. So why not? And then
I feel that it depends on the age of the professor.